Hello, it's me again. This is section 3.1 from James Stewart's Calculus Early Transcendentals book, and we are embarking on calculating derivatives without going through the long, cumbersome job of using the limit definition of the derivative. So we're going to develop some shortened rules that actually use the limit definition so that you can believe that this is the proper way to take the derivative. Okay, so first off, what's the derivative of a constant function? That derivative is going to be 0, and if you take a look at the proof, we are using the limit definition of our derivative, which is f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. And remember, that's the difference quotient, and the strategy for simplifying the difference quotient is to clear the parentheses in the top, factor out the h, cancel the h's, and then use our limit rules to calculate the derivative. Well, if our function is f of x equal to c, then f of x plus h also equals c, and f of x plus h minus f of x is c minus c, and we have 0 over h. And since that h at the moment, before even taking that limit, 0 divided by any number is equal to 0, and then the limit of a constant is a constant, and so the limit of 0 does equal 0. And it does make sense because if our function is a constant, let's say this is where our c is, then our function looks like a straight line, and that is c equal to f of x, and our straight horizontal line has 0 slope everywhere, so it makes sense that f prime of 0, or f prime of c is going to be 0 everywhere. All right, the derivative of x is going to equal 1. And if we just take f of x is equal to x, then f of x plus h is x plus h. And minus x, we can cancel our x's. And so we would have the limit of, as h goes to 0, of h divided by h. And h divided by h is going to give us 1. And the limit of 1 is equal to 1. So the derivative of x is equal to 1. And the power rule, so if we've got x raised to a number, we're actually going to use the binomial expansion. And if f of x is x to the n, then f prime of x is going to be the limit as h goes to 0 of f of x plus h minus f of x over h. And so we've got x plus h to the n, and f of x, and x plus h to the n is equal to this monstrosity. And you'll notice that every single term, except for the very first term, contains an h, right? So we see an h factor, we see h squared, we see h to the n minus 1. After the first term, we start including h, and we start dropping one power of x. But and then when we go to subtract minus x to the n, we can cancel our minus x to the n, and plus x to the n is 0. So that our very next step would be to, let's factor out h from each of the terms. And the only one that still contains, that does not contain h any longer, is going to be the very first one. Notice that in the very first one, we only had one h. And when we factor that one h out, we don't have any more h's there, but every single one of the other ones does. But what do we do with that difference quotient? We're always on a mission to cancel that one factor of h so that we don't end up with that in the denominator. And notice everywhere else, we do have h's, right? We have an h here, we have an h here, we have an h here. And when we plug in our 0, all of them go away. This is going to 0, this is going to 0, this is going to 0, and we're just left with n times x to the n minus 1. And that's a very, very useful tool, and we will use that a lot. Okay, so that's our general power rule. So how do we employ that, or how do we do that? We say, okay, f prime of x, we're going to take the 5 down, and then we're going to subtract 1. So this is going to be 5x to the 4th power. for g of x equal to square root of x, we can use our exponent rules and say that this is equal to x to the 1/2. And so our g prime of x, what do? We take our exponent down and we subtract 1. And so I can simplify this. X 1/2 minus 1 is to the minus 1/2. I can take that downstairs and call it 1/2 times x to the positive 1/2. And I can replace it with its radical. So our g prime of x is going to be 1/2 times root x. Okay. The next example, h of x there is pi to the 3rd power. Pi is a constant number. So this pi cubed is going to be a constant, right? It is roughly equal to 3.14159 to the 3rd power. And what is the derivative of a constant? 0. Good. So don't be fooled by that. All right. Now we have some what I call the algebra of derivatives. If we've got a constant number, the derivative of a constant times a function is equal to the constant times the derivative of the function. Good. Or we can write it as the derivative, or c of f of x prime is c times f prime of x. All right. And so here's that proof. If we just let g of x equal c times f of x, then the derivative g prime of x is going to be g of x, limit as h goes to 0, g of x plus h minus g of x over h. And we just plug in our value c of f of x plus h minus c of f of x. We can factor out the c. And then we can take that constant out of the limit. And so we can see that that's equal to c times f prime of x. So we can extend our power rule to include monomials or even polynomials. So we've got here, in just taking our f prime of t, we still have the 3, and then I'm just going to take the derivative of t to the 5th, and remember that's t to a number. We can take the exponent down, and then we subtract 1. So, and then I can simplify that. 3 times 5 is 15, and t to the 5 minus 1 is t to the 4th. And that's what our f prime of t is going to be. That's not so hard. You do want to get into the habit of going from this step to this step. And so you can just take 5 times 3 and say it's 15, and then just remember to subtract 1. Good. This one, I can use my exponent rules and say that this is t to the 1st power times t to the 1/2. And that's going to be t to the 1 plus 1/2, or t to the 3/2. And so if I take my g prime, that's going to be take the exponent down and then subtract 1. And 3/2 take away 1 is going to be 1/2. And so then I can say that this is going to be 3/2 times the square root of t. Good. We do not want to take the derivative of t times the derivative of root t. It's just the derivative of a constant times a function is the constant times the derivative of that function. How would we do this one? Remember, your index is always your denominator. So I can rewrite this as, and I can say that this is 4/3 times 1 over the cube root of t to the 4th. I can say that this is 4/3 times 1 over t to the 4/3, recalling that your index is your denominator of your radical. And then I can change this to 4/3 times t to the minus 4/3, and that is my h. So what is my h prime of t? It's my constant times the derivative of my function. And remember what my derivative is. I'm going to take down my exponent. I'm using the power rule. And then I subtract 1, right? I can go my 4/3 times negative 4/3 is minus 16/9. And minus 4/3 minus 1 is minus 7/3, right? And this is going to be t to the minus 7/3. So I can still take that downstairs, and I can say that this is minus 16 over 9, and I can put it back in my radical, and I can say that that's t to the 7th. And if you wanted to simplify that radical, you can, or in this case, you can just leave it the way that it is. But that's what your answer is. All right. We do have a sum and a difference rule. If we've got f and g are differentiable functions, then the derivative of a sum is the sum of the derivatives. And they take you through that proof, and notice that we are starting with the limit definition, and they are just using a series of algebraic operations to split them both up, and using splitting up fractions, right? We can split up fractions also. And then so we do see that the derivative of a sum is the sum of the derivatives, and that allows us to take derivatives of polynomials and various terms. We can also take higher order derivatives. So remember, what is the derivative here? We can rewrite this as x to the 5th minus 3/4 x to the 4th. And so we can use our rules of sums and differences and take our derivative here. So our first derivative, we're just going to take them term by term. So this is x to a number, so we're going to use our power rule, and we can say that this is 5 times x to the 5 minus 1. This is a constant times a function, so the derivative of that is the constant times the derivative of that function, and the derivative of x to the 4th is 4x to the 4 minus 1. So we can write this as 5x to the 4th. We can cancel these 4's, minus 3x to the 3rd. That's our first derivative, but they want us to find the second derivative, so we're just going to take the derivative of the derivative. So this is the second derivative, and we're just going to repeat. This is going to be 5 times the derivative of x to the 4th, and the derivative of x to the 4th is, we take the 4 down and we subtract 1. And then we have minus 3, and what's the derivative of x cubed? The derivative of x cubed is take the 3 down and then subtract 1. So we can simplify. 5 times 4 is 20, 4 minus 1 is 3, minus 9, and 3 minus 1 is 2. So our second derivative is going to be 20x cubed minus 9x squared. Is that good? So you do want to be able to go from this step down to this step. So just get used to saying, okay, 4 times 5 is 20, and then subtract 1 from 4. 3 times 3 is 9, and then subtract 1 from 3. Good. And this one looks a little funky, but it's not. Okay, we can write this as root 2 times x to the root. So that says times in there, right? So let's just go ahead and take, that's just a constant times the derivative, or times x to the number. So what's our derivative? Our derivative is going to be that constant, and now we're just going to use that power rule. We're going to take the root 2 down, and we're going to subtract 1. This one up here is just x to the 1/2, so we're just going to say plus, we're going to take 1/2 down, and we're going to say 1/2 minus 1. And then plus root 2, the derivative of a constant, is 0, right? And now I'm just going to clean these up. Root 2 times root 2 is 2. And I'm still just going to keep that as root 2 minus 1. This is plus 1/2 x to the minus 1/2, and then plus 0. So finally, my derivative here is just 2x to the root 2 minus 1 plus 1 over 2 root x. Good. Do not be alarmed by weird looking expressions. Just recognize what you're looking at. Good. All right. Here, in this case, since we have not introduced ourselves to the chain rule, the way that we would handle this next example C is to expand our polynomial. So this would be 1 plus 3t times 1 plus 3t. And if I used distributive property twice, or the FOIL method to expand, I would end up with 1 plus 6t plus 9t squared, right? And that's my f of t. So what is my f prime of t? My f prime of t is going to be, what's the derivative of a constant? 0. What's the derivative of 6 times t? 6 times the derivative of t, and the derivative of t is 1. So we can use this as 6 times 1. And what is our derivative of 9t squared? It's going to be 9 times 2t, because the derivative of t squared, you take the 2 down, and then you have 2 minus 1. So simplifying this, we get 6 plus 18t. And this is a lot faster to calculate derivatives than using that limit definition, isn't it? I think so. All right. This one here, it says find dq dp. So remember, the variable in the denominator is telling you what your variable is that you're taking the derivative with respect to. So a here is not the variable. You can look at that as a constant. What we would want to, in this case, do is split up the fraction so that we have two separate terms and then take the derivative term by term. So this is going to be a over p minus p squared divided by p. I can call this a times p to the minus 1, and this is going to be p squared divided by p is just going to give me 1p. Good. And that is my q of p. So what is my q prime of p? That a is just my constant, right? And now here I am taking the derivative of p to the minus 1. I can take the minus 1 down, and then I'm going to subtract 1. And then I subtract, and what is the derivative of p? Is just 1, right? The derivative of x is 1. The derivative of p with respect to p is dp over dp, and that is 1. And here I can simplify, and I get minus a p to the minus 2, take away 1, and that can be minus a over p squared, take away 1. And that is my derivative. Okay. I'm going to stop here, or actually just to ask, like, what is my derivative f prime of x if f is x cubed plus 3x squared? My f prime of x is going to be 3x squared plus 6x, and taking that derivative of a constant as the constant times the derivative. And it's asking, and in part B, at which points does f of x have a horizontal tangent? Horizontal tangents mean the slope is equal to 0, right? Horizontal lines have a slope equal to 0. So remember, f prime of x is going to give me the slope of the tangent line at x, right? So when would you have horizontal tangents? Would be when f prime of x is going to equal 0. So we have f prime from above is 3x squared plus 6x is equal to 0. I can factor out a 3x, and I'd get x plus 2 equal to 0. And we can use our 0 factor property. Then I can say then when 3x is equal to 0, or when x plus 2 is equal to 0, and solving for x here, when x is equal to 0, or when x is equal to negative 2, that's when I would have horizontal tangents. And if you plug those values into f prime, you would get 0 slope, and you would have a horizontal line there. Okay? And it says find the equation of the line tangent to f of x at x equal to 1, then graph the function with the tangent line. I might not take the liberty of graphing, but how do you find the equation of the line tangent to f of x at x equal to 1, we would first, we know that f of x is equal to x cubed plus 3x squared. We know that f of 1 is going to be 1 cubed plus 3 times 1 squared, which is 1 plus 3, which is 4. So our point on f of x is the point 1, 4, and we want that to be our x1, y1, right, on our tangent line. Our slope of the tangent is going to equal f prime evaluated at 1, or you would say dy dx at x equal to 1. And we know that f prime of x is, what was it again, 3x squared plus 6x. So our f prime of 1 is going to be 3 times 1 squared plus 6 times 1, and that's going to give us 3 plus 6, which is 9, and that's going to be our slope m. Good? So we have a point, we have a slope, so we can say the equation of the tangent is just going to be y minus y1 equal to m times x minus x1, and we want to plug in our values that we have. Our x1, y1 is the point 1, 4, and our slope is 9 because it's f prime evaluated at 1, and so we're just going to plug in those values. Good. And then we would solve for y to put it in slope-intercept form. So our y1 is 4, our slope is 9, and our x1 is 1. And we can say that y here is going to be 9x minus 9 plus 4, or 9x minus 5. And that would be the equation of our tangent at x equal to 1. We'll be doing a lot of those throughout the course. What's the equation of the line? Mainly because it's the tangent line is a nice approximation to your curve for values really close to that point. And so it'll be important to be able to calculate the equation of the tangent line. All right, I'm going to stop here, and I will do more motion problems and stuff in future videos.